Section 8.2 talks about composition and inverse transformation. Now, to talk about inverse, remember, if we're talking about a function f is a function if the first coordinates, the x coordinates, do not repeat. For you to talk about an inverse, you want a function to be 1-to-1. What does 1-to-1 mean? 1-to-1 means a relation represents a 1-to-1 function if it is a function in which the second coordinates, the y coordinates, do not repeat, which means for every one x there's exactly one y, and for every one y there's exactly one x. So in a function relation, you could have two x values mapping to the same y, meaning like f of x equal x squared, for example. And the range, so this is the domain. I'm writing it this way because that's how it's going to look for us. There's the range. You could say if you put 1 in there, that's going to map into 1. And if you put -1, that's going to map into 1 as well. That's a function. This relation, y equal x squared, is a function. For every one x, there's one y. It doesn't say the other way around. But this is not 1-to-1 because going back, that wouldn't work. So for a 1-to-1 relation, for every one x, there's one y, and for every one y, there's one x. So let's get this out of the way. Now we're going to talk about a 1-to-1 relation for a transformation, linear transformation. Let the transformation go from v to w. So from v to w. If t is a linear transformation from the vector space v to the vector space w, then t is said to be 1-to-1 if t maps distinct vectors in v, we're talking about vectors now, not points, into distinct vectors in w. All right, well, distinct in v and distinct in w, kind of like distinct domain and distinct range. That idea is pretty much you played with, you did horizontal line tests and all of these things. The idea of onto is a bit different. If v is a map from v to w, the same as the top, is a linear transformation from vector space v to w, same thing, then t is said to be onto or onto w. Notice, onto w, if, we'll just say onto though, if every vector in w is the image of at least one vector in v. That would be onto right there. That relation f of x equal x squared would be onto, because every point you're going to get in here could be mapped to at least one. So kind of you're looking at the range and saying, okay, if I take a point in the range, can I find a point in the domain that maps that? Kind of like saying, given for onto, look at B and think, can I find f of a that gives me b? If that's the case, we say the relation is onto. So this relation right here obviously is 1-to-1. For every one x there's one y, and they don't say that, but it is onto as well, because look, every point in the range happened to have at least one point in the domain. This relation right here is not 1-to-1 for sure, and 1-to-1 we put 1-1. But this relation is definitely onto. Why is that? Look at the points in the range, or in W. Do you notice there's at least one point in V that maps to those? This is if we're talking about discrete. If we're talking about continuous, this would be onto for sure, because everything in W has been mapped to something in V. This, however, would not be onto. Oh, they do say that. Because if I take any of these points, I notice they're not mapped back to V. V is mapped to this rectangle right there, and we left all of these values out. So that wouldn't be onto. A one-to-one relationship for continuous is very challenging. So this is a bit of an explanation just because it's kind of, algebraically, I'll show you what that means. The idea of a one-to-one linear transformation can be expressed in two ways. Remember, one-to-one means for every one x there's one y, and every one y there's one x. Now, if a relation is one-to-one, you could find an inverse. Let V be a transformation. Let T be a linear transformation from V to W. Let it be one-to-one, right? Oh, actually, is one-to-one if and only if for every vector in W in the range of T, there's exactly one vector such that the transformation of V equal W, kind of like saying f of A equal B. And T, the transformation V from V to W is one-to-one if and only if T of U equal V implies that U equal V. We do that in algebra. We say f is a function if whenever f of A equal f of B, then A equal B. A lot of work to do that. Normally we just graph it and use the horizontal line test to show it's one-to-one. So one-to-one seems to be simple compared to onto, but we have a couple of theorems that are make onto relation easier to check. If T is a linear transformation from V to W, then the following two statements are true. T is one-to-one, and the kernel of T equals 0. If the kernel of T equals 0, if the kernel of the transformation equals 0, then it is one-to-one. That's what that means. If the linear transformation from Rn to Rm is a matrix transformation, then the transformation of A is one-to-one if and only if the columns of A are linearly independent. And the transformation of A is onto if and only if the columns of A span R sub m. So Rm. Now, we'll talk about that when I get to the examples, how to check that really quickly. And I just want to remind you really quick, if I'm taking T1 transformation, linear transformation from U to V, and T2, T sub 2 is transformation from V to W, are one-to-one transformations. If those are one, then if I take the composition, that will be one-to-one. And remember, if you take the inverse, you swap the order of those. All right. So remember that the kernel maps everything to 0. Let's start with example 3. I'm sorry, let's start with example 4. It says, determine whether the linear transformation is one-to-one by finding the kernel and then applying theorem 8.2.1. Now, you know, on a test, I wouldn't ask for that, something like that. But I'll say, you know, determine if it's one-to-one. You could use the kernel to do that. And the way you would do that, basically, you want to figure out what the kernel of T is given xy. Well, let's see. I want x minus y to equal to 0, y minus x to equal to 0, 2x minus 2y equal to 0. Well, this is implying that y equal x in every case. And if y equal x, then we're talking about xx. So the kernel of T would equal the span of any multiples of one. So T is not one-to-one. It should be 0, 0. If I look at the second problem, the same deal. I want to find the kernel of T. Let's see x and y. So I want I want the kernel of t to equal 0. So I want t of xy to equal 0. Well, let's see. Then I want 2x plus 3y equals 0. That means y equals, oh, x, it doesn't matter. Y could be 3. X would be negative 3y divided by 2. So we say here, kernel of t is the span of, if I let y equal 1, negative, any multiple of that will do. So this is not 1 to 1. And why is that? Because we want it to be simply 0. Let's look at the third example. We want xy such that the kernel will be kernel of t. I'll get that at the end. I want t of xy to equal 0. That would happen if x plus y equals 0 and x minus y equals 0. And in that case, I'll get 2x to be 0, x equals 0. And if you put that up there, y would be 0 as well. So here, I know that the kernel of t is the 0 vector. So t is 1 to 1. So if I get anything, then both of them being 0, we'll say, guess what? That's not 1 to 1. Okay, here we are. Let's look at number 6. Let's talk about matrices. Determine whether multiplication by A is 1 to 1 by computing the nullity of A and then applying theorem 8.2.1. 8.2.1. We want the kernel to be 0 and t to be 1 to 1. Well, let's see. If I take negative row 1 plus row 2 in row 2 and negative 3 row 1 plus row 3 in row 3, what would happen? So we have a negative 2, that's a 0. Negative 2, wait. Negative 2 row 1 plus row 2. Negative, that's a 3. And if we multiply by negative 3, that's a 0. And negative 6, that's a 3. And if we take negative row 2 plus row 3 and row 3, so nullity of A is 0 because we got 2 pivots, right? And we have 2 of those. So 1 to 1. Multiplication by A is, oh boy, 1 to 1. Okay, actually, it's more of this. I don't, why did it say 8.2.1? 8.2.3. Transformation of A is 1 to 1 if and only if the columns of A are linearly independent. That's all. Okay. And how about here? If we take this, excuse me. Okay, well, we notice if this is x1, x2, x3, so again, we're taking set ax equals 0. Well, here, we know that the nullity of A is 1, right? 3 pivots, 4 variables. X3 is free. right? So we say multiplication by A is not 1 to 1. All right. Come on. Okay, we go. So use the given information to determine whether the linear operator is 1 to 1, onto, both, or neither. Well, let's look at this. We have a transformation from V to V. The nullity of this transformation is 0. Automatically, T is 1 to 1. Now, wouldn't the rank of T equals the dimension of V in this case? Since the nullity is 0, remember, rank of T equals dimension of V plus, no, dimension of V equals backwards. Dimension of V will equal the rank of T plus nullity of T. Okay, so it was N equal, remember, the rank of A plus nullity of A. Well, what's taking the place of N? N were the number of linear independent vectors. Well, here, if the nullity is 0, then we know those are equal. That implies it is onto. On B, if the rank of T is less than the dimension of V, well, if that's the case, that means rank of T is less than the dimension of, so let me see again. We say dimension of V equals the rank of T plus nullity of T. Now, if they say the rank is, or the dimension is greater than the rank, well, just let me think about that for a minute. Okay, I got it, yeah. If the dimension of V is greater than the rank, that means the nullity is not 0. And if the nullity is not 0, that means the vectors are not linearly dependent. Therefore, it's not 1 to 1. There we go. That makes sense. And since the rank of T is less, automatically it's not onto either. There'll be some vectors in the image that do not have a pre-image. All right. Not have, that do not map to a pre-image. Number 10, show that the linear transformation, okay, from P2 to P2, remember what those are. A sub 0 plus A sub 1x plus A sub 2x squared, right? Define the transformation of P is simply P of x plus 1. Okay, so you shift the x's by 1. Is 1 to 1. Do you think the transformation is onto? Well, let's see how this works. If I take the transformation 1 to 1, so if I take the transformation of A sub 0 plus A sub 1x plus A sub 2x squared, that's simply A sub 0 plus A sub 1 into x plus 1 plus A sub 2 into x plus 1 squared. If I set that equal to 0, I'm trying to figure out what the kernel of T is, right? You set it equal to 0. The only way that will work if a sub 0 equals 0, a sub 1 equals 0, and a sub 2 equals 0. So the kernel of t turns out to be the 0 vector. Therefore, t is 1. So in this case, is it 1 to 1? If I take dimension of P2 would be the rank of T plus the nullity of T. But if they are all linearly independent, that's 0. That would indicate that the rank and the dimension of P are equal, so yeah, it is onto. (14) Use theorem 8.2.3 to determine whether multiplication by a is 1 to 1 onto both. Justify your answer. All right, well, let's look at this. If I look at multiply this by a -3, that will be a 9. That wouldn't be a -4. So here we know that the columns of A are linearly independent, right? So we say that multiplication by A is 1 to 1, and that checks. Now for the onto part, 8.2.3 again is right there. So again, if the columns are linearly independent, it is 1 to 1. Okay. The transformation of A is onto if and only if the columns of A span Rm. Rm is the image. Well, let's see. These vectors represent what? These vectors are in R3. So if I'm going to go to R3 and I only have 2 vectors, right? Since we only have 2 columns, they do not span R3. And therefore, multiplication by A is not onto. And if I look at the next matrix, well, clearly if I multiply this by a -1, I'll get that. So those are linearly dependent columns, therefore it's not 1 to 1. That's simple. Now, can it still span R3? There are 3 of them, so one could go out, that's not a problem. I need at least 3 linearly independent vectors to span R3 because these belong to R3 each. If I multiply this by 3, I'll get that. So that's a linear combination. So there are 2 linearly independent vectors. Again, do not span R3 because that's what they're going to map onto. Therefore, multiplication by A is not onto. I'm just going to move a few things around. And we get to this one. Again, if you multiply this by -3, you will get that, or the determinant equals 0, however you want to decide that. So those columns are linearly dependent, therefore not 1 to 1. And again, the same idea. If one was a multiple of the other one, then that does not span. Those are members of R2, do not span R2, therefore the multiplication by A is not onto. And here I could see that I have 3 pivots, right? So the columns of A are linearly independent, and therefore our bases for R3, which means this is automatically 1-to-1 because they are linearly independent, and they form basis for R3. It means it is onto as well. And just a quick practice, we did this before. Let's get this composition transformation out of the way. If I take the transformation, the composition of the transformation on x, y, that would be t sub 2 operating on t sub 1, 2x minus 3y and x plus y, and that would be so let me fill in the blanks. So the yellow part minus the blue part, and the blue part plus the green part. So the yellow part was 2x minus 3y and minus 3y, and the z component, that will be 2x plus 3y and x minus 2y. There you go. And that's pretty much it for this section.